All right, welcome back. We're going to try to get introduced to our next to last unit of the year. We just finished up and had our test over mechanical waves. Largely, we're talking about sound waves and things that are similar. We introduced a little bit of things about electromagnetic waves, but the next several weeks are going to be going into a little bit more depth about electromagnetic waves. The illustration on the front shows all the different types of electromagnetic waves that we will discuss. So hopefully by the end, in about 10 minutes, you'll be a little bit more familiar with all of these. But again, a lot of these things are things that you know about a little bit: radio waves, microwaves that we cook with, infrared, which you might not be quite as familiar with, visible light, which allows us to see things, ultraviolet light, which we know is invisible but can cause skin damage, X-rays that allow us to see the bones in our body, and gamma rays, which are the most energetic, can be dangerous, can also be used in medicine to kill things to benefit us, but they have the most energy and have the most ability to cause changes in things. So I'm trying to answer a handful of questions, and again, just encourage you to take notes on this and take pictures of them at the end. That way you can get some extra credit, but also that you'll have your information in front of you. I'm going to answer these questions. What's the difference between mechanical and electromagnetic waves? We should probably already know that a little bit. What are some examples? I just went over some of them. And then look at the relationship again between frequency and wavelength of all the different electromagnetic waves, because the rules that we had in the previous unit still apply. And then we'll talk about the speed of electromagnetic waves. And the vocabulary is nothing really new here. I'll just use EM for electromagnetic, just saves me some typing. So when you see that, hopefully you can remember that's what that is. So again, if you need to pause and write any of this down or at any time, please take advantage of using the video to be able to pause, rewind things when necessary in case you don't quite get something. So first of all, what is an electromagnetic wave? So I'm going to put a few things up here and then talk about it just a little bit. So they carry energy and momentum through space. Now don't just go through space. They can go through air and they can go through water, and in some cases they can go through solids. But they move energy. They can travel through the vacuum of space, so they don't need a medium like sound waves need a medium. And they're caused by accelerating electric charges. Now, if you don't quite get any of this, that's okay. But I know some of us like to kind of say, well, what's causing all this stuff anyway? And to be quite honest with you, some of this is probably over my head, because it takes a lot of different concepts in science and kind of puts them together. And also it's largely involving things that are invisible to us. And so to think about what's actually happening can be a little bit overwhelming to our brain. So let's start with what's causing it. It's caused by an accelerating electric charge. So let's go back a little bit through science for the last couple of years. If it's an electric charge, then that could be that's basically a moving electron. All right. So where do you have a moving electron? Basically, you have moving electrons in everything, because everything's made of atoms. Atoms have protons, neutrons, and electrons are constantly moving. And remember, back in the fall, things are accelerating when they're changing directions. So effectively, electrons, if they're moving and they're not moving in a straight line, they're constantly accelerating. Thus, they're creating electromagnetic waves, which means that anything that's made up of atoms is creating electromagnetic waves. You are made of atoms. You're creating electromagnetic waves. And so those things they're around us all over the place. Again, most of them are invisible. And another key aspect of it is the name electromagnetic, is that these types of waves, such as light, as they travel, they're creating a magnetic and electric field, as the name says. So again, it's an electromagnetic wave. And the reason why, again, because it creates an electric field, which goes back a few units ago. It also creates a magnetic field. And you might remember from electromagnetism that electricity and magnetism kind of go hand in hand, because moving a magnet can cause electricity, and moving electricity can create a magnetic field. And so these two things kind of go hand in hand. So one of the things we see when we have an electromagnetic wave moving is it has this oscillating, again, we use the word oscillating last unit was one of the words in our formula sheet. Oscillating just kind of means moving back and forth. So there's an oscillating electric and magnetic field associated with this type of wave. And again, this kind of wave is a little bit different than a sound wave. It's a little bit different than an ocean wave. And a lot of people would kind of classify them as not necessarily just being a wave, but they're just fundamentally something different. Thinking of them as a wave helps us just to kind of understand a whole lot of other things about them. But I think, again, if people were studying this really deeply, they kind of get into thinking about them more mathematically than they do just drawing them as a wave. So again, if you didn't quite get any of that, that's fine. But again, the cause of it is electrons moving back and forth, or electrons accelerating, or electrons moving. That's what's creating the electromagnetic wave that causes it to be able to move until it kind of bumps into something else. There's a whole lot of different kinds of electromagnetic waves. We largely classify them based on their wavelengths and frequencies. All right, so we did that with sound. Remember, so sound can have different wavelengths and different frequencies, and we can hear that as different pitches. And electromagnetic waves have different wavelengths as well. And the different wavelengths are caused just like we did with our slinkies. Like we could move the slinkies back and forth more rapidly, and that's going to change the wavelength. The same thing can happen with an electromagnetic wave. So if you have more energetic electrons, in principle, you're going to get more energetic waves, and that's going to relate to kind of the shape of the wave that we get to. So if we get different electron vibrations, we're going to get different wave patterns. Simple as that. So again, frequency and wavelength are going to go along with that, and we'll try to relate that to energy as well. So in the introductory slide, there was like 7 different electromagnetic waves, and there's a little guy up here in the upper corner of the screen. If you're not familiar with him, this is Marvin the Martian. I needed to find an illustration for a Martian, so it's the best one I got. You might be familiar with him from Bugs Bunny, or you might have no clue who Marvin the Martian is. He was always trying to get Bugs Bunny when Bugs Bunny was in space for some reason or another. Don't know why Bugs Bunny was always in space. And Marvin the Martian talked like this. Sometimes he would get very angry and say, "This makes me mad." So there you go. There's your entertainment for the day. The reason I have them up here is so that you can hopefully have a memory device to help you remember the order of these, because if you read from left to right across the waves, there's radio waves, there's microwaves, there's infrared, there's visible, there's ultraviolet, there's X, and there's gamma, and sometimes the order of these is hard to keep straight. So we have now a nonsense sentence. It's not really nonsense. We can remember it, particularly if we have the image of Marvin the Martian here. Raging Martians invaded Venus using X-ray guns. If you can remember the sentence, then the first letter is supposed to help us know the order of our waves. So R for radio, M for microwave, I for infrared, V for visible, U for ultraviolet, X for X-rays, and G for gamma. So again, go back to this. Raging Martians invaded Venus using X-ray guns. I would encourage you to pause the video for a moment and to at least sketch out this picture. What we want to notice here is that as we go from left to right, from radio to gamma, we see that the length of the waves shrink. We don't need to know anything about the actual lengths themselves. You do get the idea that radio waves are about 1 meter in length. And then when we get down to gamma waves, they're 10 to the minus 12th. So that's 1 over 10 to the 12th, really, really tiny. And so the wavelengths, as we go from left to right, shrink. So the wavelengths decrease, which means their frequency is going to increase. And the other thing we're going to see with this is as the frequency increases, the energy is also going to increase as well. The way that they're drawn right now, they all have the same amplitude, but they're getting closer together, which means that there would be more waves hitting per second. The period between the waves is going to be smaller. So as we move towards a gamma wave, not only do we get higher frequencies, we also are going to get higher energy. So again, would encourage you to stop this and just kind of at least sketch out a shape of the waves getting smaller, and then the order of these. Again, you don't really need to know the wavelengths in meters, and you don't really need to know, this stuff here on the bottom, but we do want to know that the wavelength decreases and the frequency goes up. All right, what's the speed of electromagnetic waves? All electromagnetic waves travel at the same speed. Doesn't matter if it's a radio wave or X-rays, gamma, visible light. They're all traveling from point to point, from the sun to the earth. It's going to take them the same amount of time to get there because they're traveling at the same speed. So speed is always constant, just like we've talked about with sound waves. Sound, as long as the air temperature doesn't change, sound waves are always traveling at the same speed. Light is always traveling at the same speed unless the medium changes. So in a vacuum, this is in a vacuum through space, The approximate speed is 3.0 times 10 to the 8th meters per second. That's a big number, again, because remember, times 10 to the 8th is 10 times 10 times 10, 8 times. And so, what we see here then is, like with the previous slide, because the speed of all these waves stays the same, what has to happen is there's an inverse relationship between wavelength and frequency. Okay, so as the waves get smaller, the frequency is going to go up, because again, we still use the same formula that velocity equals wavelength times frequency, same formula we used for several weeks, but now we're going to be applying it to light. Okay. So I wanted to take a moment, see if you could test yourself, because you hopefully had either jotted this down or you didn't. And if you didn't, you can test yourself to see how your memory is right now to see if you can put these in place. So again, I'm going to ask you to pause the video and see if you could fill in 1, 2, 3, 4, 5, 6, 7. Could you, and also fill in the blanks down here with wavelength, frequency, energy. And this was another one. It says penetration and dangerous, which was not on one of the previous slides, but you should be able to infer it. So again, good time to pause the video and work on this. Once you have this finished, you should have this order again: raging, Martians invaded Venus using X-ray guns. There you go. So there's our order. Again, as you go from left to right, the wavelengths are going to get smaller, which causes the frequency to go up. And because we're having a higher frequency, we're having more energy. And because we have more energy, we have kind of more penetration. Think about your body. Ultraviolet light could damage our skin, but that's about it. X-rays can go into our body, but they don't go through bones. That's why when we get an X-ray made, we're basically seeing a shadow of our bones, because the X-ray goes through the soft tissue of our bodies, but it doesn't go through the hard bones. And so the film behind it is getting exposed where the rays go through your soft tissue, but they're not being exposed where the bone is. And then gamma is going to be our strongest one, because again, it's X-ray guns. And so G is going to be at the very end. So I just went over it, but do you still remember? Do you still remember? What's our thing? So we got raging, Martians, right? So that's radio, microwave. Invaded, infrared. Venus, visible. Using, ultraviolet. X-ray, X-ray. Guns, which is for gamma. So hopefully, again, you can take those 7 words, make the sentence out of it with Marvin the Martian, and be able to remember kind of the order from lowest energy up to highest energy. All right, so again, hopefully we know now some better differences between mechanical and electromagnetic waves. We know 7 examples of electromagnetic waves. We kind of get an idea on the spectrum, what's the relationship between frequency and wavelength, which of the electromagnetic waves have the greatest frequency, lowest frequency, biggest wavelengths, smallest wavelengths. And then we know the speed of electromagnetic waves is 3.0 times 10 to the 8th meters per second, and that does not change regardless of the wave that we have. All right, so thanks for watching. Probably have some more assignments to do. Take care.